Hello students, let's do a thermal equilibrium problem. We've got a hot 250 gram chunk of copper, it's also 250 degrees Celsius, and we're going to put that into some water which is 22 degrees Celsius, so room temperature, slightly warm. And so when we put those two together, we want to find what our final temperature is going to be. Here's our only equation that we're going to need. The hot copper is going to cool down, so I'm going to write delta T1 because this is material 1. To show that it's going to cool down, we'll do 250 degrees Celsius minus T, showing that it's losing temperature. And then our other material, the water, delta T2, we'll do the opposite. It'll warm up. So I'm going to write it in the other direction, the other way. T minus its starting temperature, 22 degrees Celsius. So once we have those, now we have essentially its conservation of energy. We've got heat lost over here will equal heat gained over here. So I'm going to write this as mc delta T equals mc delta T, because that's what Q equals, mc delta T. This side is for substance 1, this side is for substance 2. So now, you can't really see the 1 right here. So now instead of writing the delta T1, I'm going to write what delta T1 equals. So we'll rewrite this as M1 C1 and then 250 degrees Celsius minus T equals M2 C2, and I'm going to write T minus 22 degrees Celsius. So from here, we're just going to put all the numbers in. We're going to put in our 250 grams for our copper. The specific heat capacity is up there in that box, so it's 0.386 joules per gram degrees Celsius. And then we're going to write our 250 degrees Celsius minus T for our delta T. We'll do the same thing for the water. So 500 grams, and then we've got our 4.186 joules per gram degrees Celsius, and then T minus 22 degrees Celsius. So unlike most of the other problems where we should keep our units all the way through, just to simplify this, and because the units will all cancel, the only ones that we need from this point are degrees Celsius. So we're going to multiply those two numbers and those two numbers to get started. So when we multiply those together on the left side, we get 96.5, and then I still have 250 degrees Celsius minus T. On this side, I have 2093, and then I have T minus 22 degrees Celsius. All right, and we have a little bit more multiplying to do now. We'll multiply these two numbers and those two, these two numbers and those two. So we get really big numbers, but it's okay, we'll take care of those at the end. So our first multiplication, this gives us 24,125 degrees Celsius. That would be normally very hot, but our final answer won't be anywhere near that. And then we have 96.5 T equals, on this side, 2093 T minus another large one, 46 degrees Celsius. So now we have to sort of combine our like terms. We'll keep the T's positive, so I'll add 96.5 T to both sides. And then I'll add my temperatures, 46 degrees. And we can see that those go away and those go away. And so we're left with, on the left side, 70,171 degrees Celsius equals 2,189.5 T. And to get T by itself, we'll divide both sides by 2,189.5. Those cancel here and here. And what are we going to be left with? Our final answer. T equals 32 degrees Celsius. So we started with very hot chunk of copper at 250 degrees Celsius, and then we plunged it into 500 grams, which is 500 milliliters of water, right? Just a beaker. And the temperature of both only went up 10 degrees from the water's temperature. Right, that is the power of water's very, very high specific heat capacity. So that's how we do our thermal equilibrium problems. Give those a try, and I will see you in class.